We have a lovely lady from ESRIC, and again, you may know her already. She's a face that's been around for a few years now. It's Vibha Levin Prabhu, and she's going to carry the next session, chair the next session, handling Lunar Regolith, transport and processing technologies. Thank you.
Thank you, Lisa. Thank you very much. Good evening, everyone. I welcome you to the last session of Day 2 at Space Resources Week 2025. As space agencies and commercial ventures shift focus from exploration to long-term lunar presence, the ability to move, manage, beneficiate, and utilize lunar regolith is becoming the cornerstone of sustainable operations. In this session, we will explore innovative transport methods, handling technologies, a novel approach to flowability, and systems designed for particle size classification of lunar regolith. Whether you're an engineer, a scientist, mission planner, or a business tycoon, I invite you to listen to our excellent speakers of this session and see how these technologies could shape the future of lunar operations. With that, I remind my speakers that we have 10 minutes for your talk and then 2 minutes for the Q&A. I invite the first speaker on stage, Piotr from University of Strathclyde. His talk is on investigating the transport of lunar regolith simulants through vertically vibrated inclined pipes.
Okay, hi everyone. My name's Peter Watson. I'm from the University of Strathclyde in Glasgow. And today I'll be presenting some of the work that we've done on investigating how vibrations can be used as a method to transport lunar regolith upwards against gravity. So just to give you a bit of an overview of what I'm going to talk about today, I'll give you an introduction kind of into what we mean by the concept of vibration transport for ISRU. I'll present a little bit about our experiment design and then results, including the effects of 4 different kind of variables that we've investigated and their effect on the flow rate of regolith upwards against gravity. So, a bit of an introduction. What do we mean by vibration transport? Well, basically, there's been a lot of previous research where complex granular materials have been seen to elicit fluid-like behavior when vibrations are applied to them, and we'd like to extend this effect to the lunar environment. So most of this previous literature kind of focuses on simpler granular materials like monodispersed glass spheres and things, where obviously lunar regolith is a lot more complicated, so that's why there's a need for this kind of investigation to see how what we know for simpler cases extends to more complex materials. And lunar regolith is pretty complicated for these cases because it has a large particle size distribution, jagged irregular shapes, lots of friction, and get some electrostatic agglomeration. The obviously final goal of this is to be able to apply this in a space environment, and at the minute the sort of TRL for this kind of method is pretty low, so 1, 2, or 3, because we're just kind of starting our laboratory testing. So here you can see our kind of experimental setup. We've got a permanent magnetic shaker that we can use to apply vibrations. This is coupled with an accelerometer and control software that allows us to apply controlled frequencies and intensities of vibration. We can also vary the inclination of the pipe from the horizontal in the range of about 0 up to about 20 degrees for what I'll talk about today. And we've also investigated the effect of varying the inclination of the vibration device from the vertical, so as opposed to applying it purely vertically in 10 degrees, 20 degrees, and 30 degrees from the vertical. And the simulant that we're using for all these experiments is LHS1. So just to give you an idea of for the results I'm going to present, what these the tests are like for all the experiment, the results I'm going to present. We start with a fixed amount of LHS1 settled in the declined end of the inclined tube. We will then use vibration to settle the material in the bottom of the pipe, so as the start conditions are reproducible. And then we'll apply different combinations of vibration in terms of frequency, intensity, and different inclination angles, and hopefully the material will move up the tube. If the material does move up the tube, it will be transported and deposited in a box at the end of the inclined end, and then the mass will obviously be measured using a mass balance. And we'll also record all these with a camera so we can get an averaged mass flow rate. So the first sort of variable I'll talk about is the effective vibration intensity against mass flow rate. So for these experiments, the frequency is 40 Hertz, the pipe inclination's 5 degrees, and the vibration direction is 10 degrees, and we've applied inclinations in the range of 2, 3, 4, and 5G. So it's intensity, so the acceleration of vibration. What we can see here is that there's a complicated relationship here. It's not as easy as just increasing the acceleration vibration, increasing the mass flow rate. We actually have an optimum value about 3G here, where increasing it past that actually causes the mass flow rate to decrease. So you can see from these two videos here, the 3G case on the top, you see a quite nice bulk flow of material, where the material all kind of flows all at once. The whole particle size distribution flows upwards as a kind of one kind of cohesive mass. But when we increase the intensity more to sort of 5G, you get a more chaotic sort of flow, where the flow starts to, the particles all kind of separate by size, and you can't really see it in these videos, but the material is actually circulating, so it's going up kind of at the closer side and then back down the other in a kind of loop. And then we'll move on to sort of the effects of frequency versus mass flow rate. So we've investigated frequencies in the range of about 10 up to 150 Hertz at the minute, and we've found the best sort of transport in the range of 40 to 70 Hertz. So that's obviously 40 to 70 Hertz is what's presented on this graph here. So we've varied the frequency from 40 to 70 Hertz while keeping the vibration intensity constant, 4G, 5 degree pipe inclination, and a vibration direction of 10 degrees. What we can see here is the frequency has a large effect on the mass flow rate of material, with an optimum value being about 40 Hertz, which is what we use for most of the tests presented in this presentation. So to kind of, hopefully these both play, yeah, to show you like the kind of mechanism of why this happens is, again, the 40 Hertz video is the same as before, where you get an entire bulk of material moving kind of as one cohesive unit, whereas increasing the frequency to 70 Hertz causes the prevalence of the Brazil nut effect, where large particles will segregate from the bulk and move up the tube, whereas the smaller particles will not move. So it shows that we kind of need to have it all cohesively moving as one to have the best chance of transport. Now I'll present the effects of sort of pipe inclinations. This is kind of probably what the most kind of the best takeaway from this is we've managed to see flow rate of material up to 20 degrees from the horizontal. But we haven't, well, we've seen it, I'll show you in the videos in the next slide, we've seen definite mass transport up to 15 degrees, but we don't actually get any transport of material out the end of the pipe at 20 degrees. So this video is for 20 degrees of inclination, and what we can see is the material has been transported to the top of the pipe, but it hasn't actually flowed out the inclined end. So one last sort of variable to talk about is the vibration direction, so the direction, the inclination in which we're applying the vibration, and we've varied this from 10, 20, and 30 degrees from the vertical, with a vibration intensity of 2G, a frequency of 40, and a pipe inclination of 5 degrees. And we've found that actually 20 degrees of inclination, so some horizontal component and some vertical component, is optimum for mass flow rate. So that's obviously quite interesting. And then just kind of to round off the kind of key takeaways from this presentation, We've presented that vibration is a viable method of conveying lunar regolith upwards against gravity. The main results we've presented so far is we've been able to accomplish this up to 15 degrees of inclination with flow rates upwards of 3 grams per second. And this is obviously as a study to try and optimize all the parameters individually. When we combine the optimum parameters all together, there's promise that we'll be able to increase the inclination further and the mass flow rate further. It's also kind of the takeaway from this research is there's quite a complicated relationship between the vibrational parameters and its effect on the mass flow rate that still needs to be investigated. And again, we are at an early stage of development, but more testing is required, but I think the results show promise. So that's all I've got for you today. I think I've come in under time as well, so open to any questions.
Thank you so much, Peter. Questions? Yeah, please. Mike.
Wow, I get first choice. No. So, okay, here you go.
Wow, okay. So I guess, do you have any idea of what this would be like on the moon with 160 in vacuum? I assume you get much better mass flow. Are you able to kind of extrapolate to?
So obviously the hope would be that it would be better on the moon, so you have reduced gravity, and we are doing all our tests at the minute it's not in a vacuum at the minute, so there's interstitial air and things like that, so obviously the humidity on Earth will have quite a large effect on the flow rate. So the hope is that all the results that I've shown you just now will be exponentially better on the moon with the reduced gravity and obviously no interstitial gases.
Yeah, along those lines, comment versus question. Two things. One is when you go to a vacuum, you'll see greatly different results in your vibrational frequency versus mass flow rate. The other is NASA has or is about to publish work on vibratory transfer, but in a circular approach versus a horizontal tube, which is much more efficient and based on terrestrial vibratory transfer. So keep an eye on those for your next level of work, as well as your shock when you get to vacuum versus Earth. Sadly, the same team performed a 1/6 gravity demo on a Blue Origin, but for some reason it failed to turn on.
Okay, thank you.
Well, you giving it to me?
We have a question at the back.
I just wonder if there's any sort of mechanistic explanation for this, any physics, or is this just a correlation of observed, in which case you don't know what variables drive it, and any time the variables change, the data is worthless?
At the point in the research we're at, it's all just, obviously, we perform a different test and kind of see what happens. Obviously, we'd love to have some sort of physical model behind what we're seeing, because we're also running simulations in DEM as well to try and replicate what we're seeing. But at the stage of the research we're at just now, we're not able to give those kind of conclusions yet, but we are gearing in that direction and hoping to get there eventually.
Hi, thank you very much for the presentation. Did you investigate any effect of the frequency of vibration you were using with the composition of the regolith? So are you using any other simulants or just the one that you used?
We have not run any tests with any other simulant at the minute, but we do have LMS one in our lab as well, and we've also run tests with both of them in a similar kind of setup to this, but with hoppers using vibration instead of inclined pipes, and we've also run some tests by sieving the materials and seeing how the particle size distribution affects it. We don't have any sort of conclusive results on that in a minute, but it's what we're looking into as well.
Great. Yeah, we have one more question there.
Hi, that was great. That was really interesting. I'm just wondering if you've studied any other cross sections for your pipe diameters, because I would imagine that having a curved surface would probably impact how material flows rather than having like a box cross section or something like that.
Yeah, so we've got an acrylic pipe to start with, just because we're at the early stages in the research, but there's lots of things to look into in that respect. Obviously, the material of the pipe will have a large impact on it, the shape of the pipe, also the diameter of the pipe. There's a lot of research to show if we made that smaller, it could potentially increase the flow. So these are, again, the areas we're going to look into. But it's a good point. Thank you.
Thank you, Peter. Thank you very much once again. Please put your hands together for him. Our next speaker on stage, I would like to call upon Süleyman Salihler from Polimak. He's going to talk on integrated regolith handling technologies to address key ISRU gaps.
Hello, everyone. We have been working on this business in space business for 3 years. Polimak is an industrial company. We have been working about more than 45 years for handling powders, industrial sectors, including mining, chemicals, food, plastics. So 3 years ago, we have established our Polimak space business. It is only connected to handling regolith and space resources. There are several types of handling processes like excavation, collection, transport, conveying, feeding. Also grinding, separation, all of them are important processes. In the terrestrial applications, we have delivering solutions for mining and chemical, energy, environmental technologies, while at the same time, in lunar business, you have, lunar construction, lunar landing pads, launch pads, water extraction, helium-3 extraction, which is very popular these days. And what we are trying to do is, we want to enable the ISRU operations in a central way. We want to enable lots of functions in a single infrastructure. You can think like Mario Brothers. They are enabling all of the stuff in, daily life. They are trying to solve the issues about water, whatever. But here, we want to solve this for different types of lunar missions. So the idea is delivering regolith in right amount, right time, with the right size, right composition, and right temperature for different lunar missions. So what we have now is, previously, we only developed a single module that is trying to move the regolith in a better way. I will show the details. But from that point, we now come up with different modules that can handle a wide range of regolith handling needs. One of them is for conveying, horizontal and vertical and inclined conveying, stockpiling it for a storage, transloading to other, for example, rovers, haulers, whatever is needed. Also collecting regolith to feed the lunar landers. So there are lots of scientific missions that need regolith to analyze it, whatever it is, the content or composition, whatever. But they need to move the regolith from lower level to higher level. So one of our modules is just focused on that, just moving the regolith from lower level to higher level. Also, another thing is sieving, which is also very important. We have developed a system. We are now applying for a patent for that because it is a very different design, very compact size. It can change its mesh size. Also, it can be operated as a self-cleaning device, so no need to have any maintenance after sieving. Another thing is preheating and thermal processing unit. It is using Fresnel lenses to collect sunlight, increase the temperature of the regolith. So by adding sieving after that, the preheating module, we can easily feed the material, preconditioned and prepared regolith to any device like oxygen or helium extraction. This is the core of our design. There is a hollow shaft, hollow pipe, or you can say, and there is a spiral attached to the internal side of that hollow shaft. So the outer shell is rotating together with the spiral. In ordinary auger conveyors, the outer hollow pipe is stationary, but the spiral is rotating inside of it. So in this case, you are pushing the regolith along the surface of the pipe. So there is lots of force on the surfaces, and you will create abrasion. In this design, regolith is rolling. It is sliding, but the rolling effect is more than sliding effect. So we are decreasing the amount of abrasion, which is very important in terms of long duration. These are designed as a modular unit, so it is easy to extend or change the route. And you can easily design any kind of route. That is, of course, we need to have a deployment system. That is another thing to solve, but if we can solve it, we can design any kind of conveying route. These are the modules that we are developing. The conveying module is already developed. Of course, there are some things to improve, but it is already being developed, and you can see it is working on the tech demo site. Maybe everyone saw that. There are some red boxes out of plastic, and every year we are increasing the size of that plastic so to get more attention. So the idea of this design is having a rover-mounted conveyor so the rovers can easily collect and discharge the material. The good part of this is, you know, the Rasera rotating drums. There are some collection tips on the drum. After a certain amount of time, there is an abrasion on the tip. But in our design, if even there's an abrasion, that is a long pipe. So it will not fail after a certain time because this is the same along the axis. The other one is a stockpiling module. It is used to prepare a storage of regolith, even conditioned or unconditioned. In the Earth, in terrestrial business, you have wind, so many things that may damage the stored material. But on the moon, there is no wind, so you can just put them one top of each other, and you will have a stockpile. Of course, there could be some scientific things, radiation, I don't know that kind of things, but technically speaking, I hope this will work. The other thing is sensor module. I will show it in details. Sieving module and heating module. So, the sensor module that we are now designing is a simple device that has several ports on it. So you can put several analyzer sensors on a single device. Then our MDC, the modular drum conveyor, conveys the material inside of that module and feeds each sensors individually, either at the same time or one by one, depending on the type of sensor. Of course, the size and design of the sensor is very important here, but we think we can find a solution to couple several sensors. So by using that, we could easily put that sensor module on a lunar lander or a lunar rover. So we will have a single interface between the lander and the sensor module, then a single interface for every different sensor payload. This will also decrease we are hoping to decrease the total payload weight. Okay. This is a simple application showing lots of modules working all together. The idea is having a thermal energy storage system by using regolith itself. So we have an inlet module that a rover can bring the material. Then it conveys the material to a preheating module. Then we will have Fresnel lenses to heat up the regolith. Then prepare a stockpile. As the regolith is a very insulating material, the outer side of that stockpile will be an insulation material, and the core of the stockpile will be high temperature material. And we have to do the temperature analysis, you know, the heat transfer analysis, but as far as we see from the previous studies, we saw that it is possible to have a long-term thermal reserve, especially for the lunar nights. So once we prepare the stockpile, we can easily take out the material, hot material during lunar nights, use that temperature as a source of energy. Another design is using a simple heat exchanger together with an agitator to move the regolith around it, so we will have increased the efficiency of the heat transfer. We believe all of these different modules can couple together to enable different functions. Okay, what we have achieved for 3 years is, first of all, now we are a member of consortium of Astroport that is developing a CONOPS for NASA's project for lunar landing and launchpad. The second is we are working with orbital cycling for research on the use of orbital debris to manufacture our MDC pipes out of recycled material. Similar to that, we are now working with Fraunhofer. Now we have a very good project. It will be concluded, I believe, within one month. We are melting a regolith and preparing one of our modular drums. So it will possibly be one of the first spare part produced by regolith. And we will use that spare part in our conveying system. And now we are also in the cohort of startup support program of ESRIC, the first phase. Thank you for everyone in the ESRIC who are helping us, all of the consultants and experts. And we are hoping to get the award for the second phase. Then we are now working on also University of Greenwich. We are now developing a 1/6 density of regolith to simulate and replicate the lunar regolith flow behavior under Earth-based conditions. And another project with the same team is designing a very small characterization device that can measure flow properties of regolith. So you could put that device on a lunar rover, send it to everywhere, and just analyze how the regolith is behaving, how you can collect it, how you can discharge it. Another project is with Middle East Technical University Aerospace Department. Now we are working with them to establish a lunar testbed. I am over time, sorry. And the Moon Lunar Yard, we have already made several tests with our design, and our design proved itself in Earth conditions. And thank you for everyone. Sorry about overtime.
Thank you, Süleyman. If there's one pressing question we can take, otherwise we're running a bit over time. No, no problem. I encourage you. Oh, I'm sorry, there is one.
Hi, thank you very much for the presentation. That's a very interesting concept. I just have one brief question. In regards to the system, how would you envision it being actually transported to the moon? And is it reliant on existing vehicles, such as the Eclipse providers? And if not, what price per kilogram would this make it viable at scale?
Good question, but the answer is a long-term answer. I do not have that answer up till now. Thank you.
Thank you very much. Thank you very much, Süleyman. Please put your hands together once again for him. We move on to our next speaker, Professor David Karl from TU Berlin and Colorado School of Mines, who will be presenting on novel approach to increase flowability of regolith, agglomeration of powder for thermal spraying.
Test, thanks. Okay, this works. So welcome to my talk. We jumped the first page. So this paper is, of course, a collaborative effort, as we're always doing in academia. And I want to point out that the lab worker of this paper is my PhD student, Shengui He, who couldn't be here because he's writing together his thesis. So I'm presenting for him. And I want to take you a little bit towards, let's say, beneficiation, going and producing more homogeneous regolith feedstocks, okay? And it's going to be two-part. First, let's look at the motivation. So if we look at the gold standard for metallic beam-based additive manufacturing, LPBF, EBPBF, and DED, we have very defined PSDs, so particle size distributions, that we require. In this session, I don't need this motivation, but I like this image, and it's recent, and I really wanted to share it. So, we really want very defined particle size distributions, right? And to get this going, I also put an image of a very good gas-atomized metallic additive manufacturing powders, which are highly spherical, very close PSD, and the stuff, for example, that we are dealing with looks like this, okay? So, just to get everybody on board, this is what most of the talks in the community typically work with, right? If you have a very good simulant, and so on and so on. Then what can we do about it? Being like a ceramic scientist, in ceramic science, it's very, very typical to do powder granulation, right? And what we're doing here is we're using regolith simulant, then we're doing some dry milling and some wet milling, and then we produce granules. And there's various reasons for doing that. Let's look at it in a little bit. Okay, these are cross sections of these granules that we're producing. So basically, we're doing spray drying of these colloids, and we start out with a liquid, with slurries with a feed pump, and then we do gas atomization like an airbrush. And we use heated air in a drying chamber, and then in the cyclone, if we do it right, we produce kind of granules that look like this. Like the primary particles are like almost nano-sized, and then we're going to have these nice granules that every powder technologist know flow very well and have very specific properties. And here's a PSD distribution for what we're doing. Okay, so bear with me. We're working with Martian regolith simulants for this graph. So Mars global simulants, we start out raw, and we have a PSD like a D50 of 250 microns, and then if we dry mill this, we have like 9 micrometers, and then if we wet mill this, we have 6 micrometers, and then you're asking, why are you going to wet mill it? And then I'm saying, okay, let's reduce the D90 from the dry milling, okay? And also, as a ceramic scientist, we want to do the wet milling because it's very important to break up fresh silicon surfaces. That is very important for the slurry stability. And then after the spray drying, we end up with these larger granules that have like 90 micrometers and a D90, I jumped that, of like 130. But of course, we can change that depending on the parameters we're doing. And here's some SEM images, preliminary results on these granules. So we end up being quite spherical. Here on the bottom left, you see a cross-section of this multi-phase Martian regolith simulant that is dense and that we can do some really nice ceramic processing with. And the idea behind my research, if you know me or my research group, is being a ceramicist, we really like clays, right? So here we use clays as binders for this granulation. This is why it works. If you're interested in this, let's talk about this a little bit later because it's quite complex. But the reason for what we're doing is that it works, like the binder here is phyllosilicate, so clay. And 2 years ago, I presented a paper where here in this conference where I proposed the space clay economy. So I'm really trying to kind of propose we really look at these nano-sized functional materials that are just out there, and to some effort, some people are starting to get interested in this. And with Kevin Cannon, we came up with this image where we kind of looked in our solar system at sources for phyllosilicates, and the largest volume, I like this image, it's just so nice. The largest volume we have in the C-type main belt asteroids, and then we go to the Martian crust, and then Ceres has some, and maybe something that we could access in my lifetime would be some C-types near-Earth asteroids, and we're talking, of course, to the right people about that, or trying to convince them. For example, Danon here from Common Plus, and we really want to get our hands on some of these clays, right? And if we don't have these clays available, if you know my research, I'm also working on, let's say, producing this clay on the lunar surface through various means, and maybe we even find some of these clays on the lunar surface. It might all depend on how the PSR look, but please look at my previous research if you're interested in that. So what are we doing in this spray drying then? So what it's all about, what my lab is really developing here is this slurry, right? And for getting more technical, we're currently working, let's say, with a clay ratio of 25%. That is somehow comes from the amount of clay we find in Martian crust, and then we have solids loading of 48%, and we're also doing it to lunar simulants. And here we're also working with a similar system just to compare also the active parts of the Martian regolith and the lunar regolith. And we found that, for example, magnesium sulfide, the epsomite, is very, very, very important in the slurry urology to kind of fine-tune what we're doing in terms of viscosity and in terms of the storage and recovery moduli, and so on and so on. If you're interested in this, just come talk to me. We did some parameter study where we can kind of then specifically create particle size distributions that we want through, for example, variation of air pressure. Or what we also can do is, like, we vary the pumping speed, and then we get also specific distributions. Okay, so again, let's say we start out with a Mars global simulant, and then it looks like this. This is dry milled, and then we end up with spray dried granules that look like this. And we do the same, let's say, for a lunar simulant here, the Coruscant Mines one. And we end up basically with very, very, very similar results if we use similar active chemicals inside of the simulants. Of course, you can now come to me and talk to me about, okay, but we don't find the clay here and the epsomite. And okay, I get that, I agree. But let's bear with me why we're doing this, okay? Then my lab is mostly about additive manufacturing, right? So we really want to do some powders for additive manufacturing. And if you compare like the layer distribution, we have a specific lab setup where we look at layer deposition in a very special environments. And then we see the dry milled Martian simulant produces like layers that really are not very good. And if we do our spray drying, we have a very well flow optimized Martian simulant, and the same is true, basically very similar for the lunar simulant for the processing I just showed. And so we can end up with a very homogeneous layer distribution powder bed, high definition, and it's kind of obvious why that works, right? And we also did, of course, powder characterization and so on and so on. We can talk about that maybe later if you're interested in that, but we found very good compressibilities and we found decent Hausner ratios, which is a typical measure to mesh flowability for additive manufacturing. Okay, so additive manufacturing is great, let's do it later, but sometimes also a little bit boring. If we want to do some cooler stuff, let's do thermal spraying. And I collaborated with some people where we found that we can also use these powders in like a pipe transport in a typical powder hopper, and we did some thermal spraying. So here we basically have plasma and we shoot ceramic particles to powder injection onto a metallic surface or another surface and then create these ceramic surfaces, right? And this is how it looks like, or this is what you can achieve with that. It's very typical in, let's say, turbine blades. We have these ceramic thermal barrier coatings, and these would be produced in such a process. Also, of course, there's multiple kind of correlations to jet engines and all of these things. I'm sure you're aware. And this is what we were doing in a large vacuum chamber. So we put our flow-optimized ceramic regolith inside of, this is atmospheric, so you might recognize it's not a very long plasma because the guys couldn't be bothered to evacuate the whole tube, but that will come. So we were doing some atmospheric plasma spray coating, and then this is a flowchart that I'm going to jump. But we could end up with these ceramic coatings on multiple metals. So here we have aluminum metal and copper metal that is coated with these Martian and lunar regolith flow optimized kind of thermal barrier coatings that we can talk about. I'm over time, so I'm just going to go to the SEM, which are still very porous. So yeah, let's talk about it. We need to optimize it a lot. It also has to do, of course, with what multi-mineral phases we had in the starting material. But we basically found we melted, or we kind of changed the phase of the phyllosilicates, which is what we wanted to do in ceramic science. Thanks.
Thank you. Thank you so much, David. Questions? Do we have any questions in the room? Please. Mic is coming.
Thank you, David. So I was wondering, since Regolith has such low thermal conductivity, if that presents challenges in terms of the process of sintering, or if you're thinking about it for additive manufacturing, if that's something that, if you started taking a look at like what the effects of that might be.
The effects of what? I didn't get that.
The low thermal conductivity of the Regolith.
When it's spray dried, or if we do the coating?
Well, either or, I guess.
Well, yeah, we could have a long academic discussion about that. Like my PhD, like Shengui, he really likes to kind of sell it in that aspect that, okay, we have these thermal barrier coatings, so they're very porous, and then we could say they're really good in like as a thermal barrier because there's this porosity. I would try to get them a little bit more dense first, but yeah.
So it's a controllable process then,
yeah.
in that sense. Okay, that's helpful.
Thanks.
Do we have any more questions? Okay, Thank you very much. Yeah,
Thanks so
please.
much. Come talk to me later if you're interested.
Yeah, please find him and talk to him. Put your hands together for David, please. Our next presenter is Piotr Kulinowski from AGH University of Krakow, and he's going to present us the work on three-dimensional lunar regolith bucket conveyor.
Good evening. Let's back to the conveying. I want to introduce myself. I work like a professor at AGH University, and I have been designing a transportation system for mining industry for over 30 years. And for several years, I have been provided students' project according to space resources. Short introduction. We can transport loose materials with using conveyors in two ways. One way is without causing relative movement between the transported material and the conveyor's moving elements. And on the second hand, we slide materials. We're guiding the material along the surface of the true with use of structural elements like the scrapers, with the external forces like inertial force or gravity force, or with using vibrations. I know that this material is for long lecture, but not for a few minutes. But we have a lot of opportunities to convey regolith. Depending on transportation task, it means depending on the distance, depending on the ambient conditions, we can select a conveyor, whatever we want. But maybe it will be good for discussion, but during today's presentation, I focused on bucket conveyor because of low energy consumption, because of low mass, and because of dust mitigation. I want to show genesis of our concept. Few years ago, in the Colorado School of Mines organized the competition over the Dusty Moon Challenge. And we participated in those challenges in 2022 and 2023. In the last competition, we won like the space team AGH Poland. But we offer the new concept of conveying. It's a connection to type of conveyors. Pull rod scraper conveyor connected with one drive system with bucket elevator. Parameters of work of the system, it was not so great because the horizontal length was up to 10 meters, but lifting was unlimited, limited only by requirements. And analysis of work of the system showed that maybe we can improve our system. We were preparing for the next edition of competition, but it was last one in 2023. We found that we have possibility to reduce the weight of the device by shortening the rod conveyor and using them like the only pulsating feeder. And we can use the buckets not only for vertical transport, but also for horizontal. But if you want to use this conveyor for spatial, three-dimensional transport, we have to improve guiding system and we have to design swinging buckets. We go to the laboratory, we test some elements, and result of this test was that it's possible to mount the swinging bucket and move them in vertical, in horizontal sections. And the main problem was the chain, and we test the possibility of twisting this chain, and it's possible to twist in large range of angles, and we can guide spatially, but with using special guidance. And finally, you see the visualization of our laboratory test stand and some important elements which allow us to transport regolith in buckets, but in 3D space. We have superlight chain, we have pendulum bucket attachment with anti-dust seal, we have variable forced guidance with using two sprockets, special construction sprockets, and we have swinging buckets. And it works. It's a short movie from the laboratory with testing, and it allows us to say that it's possible to use a three-dimensional bucket conveyor, but the question, where on the moon? Many times during the last 2 days, you saw this possibility. Let's focus on the south pole of the moon, and we have very interesting shadowing place. It means southern craters. And I was focusing on the transportation task. It means I try to describe the profile of for our system, and I focus on the main craters. The biggest one, Howard, Shoemaker, and Faustini. How looks the profile of this transportation task? You see, we have a long distance, over a few hundred kilometers, up to 200 kilometers, but the slope angle of each crater is not so impressive. It's maximum 20 degrees. Let's find something difficult, more difficult. Let's focus on the Shackleton crater, and I set up the profile, I counted it, and what we got? We got the really impressive slope. It's inclination between 30-40 degrees, average 32 degrees, and the length for our transportation system is 7 kilometers, and height 4 kilometers. It's possible to use in this, for this conveying bucket elevator, and on this slide you see visualization, but what is special for this conveyor? We have drive unit on the sunny places, and in this place we have solar panels, batteries, and the drive unit is separated for discharge, for dust mitigation. On the bottom of the crater, you remember 4 kilometers below, we have tension unit, loading point, sifter, and it's a place for working diggers. But very interesting in this conveyor is that we can transmit mechanical power with using traction element. In this case, in our case, the traction element was a chain, but it could be rope, but it's still a very important question for us. On this slide, you can see features of our conveyor. The name of it is Lunar Regolith Bucket Conveyor 3D, Lunar Bucon 3D. And we have low energy consumption because it's the work counterweight. We just need energy only for lifting or transporting material. Of course, it will be a problem with some friction forces, but we didn't calculate it right now. It's a lightweight construction, and I think that due to a lack of atmosphere, lack of winds, rain, snows, and low gravity, we can reach several kilometers, maybe more. Capacity of this conveyor is scalable. We can increase the number of buckets, we can increase capacity of each bucket, and we can increase the speed of traction element. We achieve this dust mitigation through the gentle conveying, because we keep the regolith in the buckets, and we use for loading pulsating scraper feeder, which construction we found during working on toll recon system. Drive and batteries will be in sunny location, and we can transmit mechanical power. But the most important from my side is I don't show you the finished project, finished solution for transport. I want to show this presentation like invitation for cooperation on finding the good solution for long-distance transport system. We still have no traction element. I think that we have not, because I don't know, it will be rope, it will be chain, but we need the traction element with high resistance for harsh conditions of environment, resistance on temperature and dust impact. And I want to go a little bit back to history, because I'm coming from mining industry, and I think the first conveying devices on the moon should be like the first mining machines, simple and reliable. And the first high-capacity conveyors for transporting bulk materials over long distance was a raw bucket conveyor, and he was built in Polish kingdom in 1644 in Gdańsk. Distance was a few kilometers, but the longest ropeway bucket conveyor is up to 100 kilometers on Earth. But I think that on the moon we have more possibilities. At the end, I want to thank you for attention, and I have more slides for Q&A part. Thank you very much.
Thank you so much, Piotr. Do we have questions in the room? I think sometimes it takes 10 seconds.
Thank you for no question.
No, sometimes it takes a little while for everyone to raise hands. Lovely. We have one question here.
Hi, Marco from ESRIC. Did you make any projection or calculation on concerning this conveyor that would be on the moon? Do you have anything like that you projected or calculated that for the moon surface concerning the gravity and the payload?
I know method, it's a known method for calculation, but it's only one problem with supporting with how we support the ropes or chain, and we don't know too much about friction either. But because of low gravity, we don't need so many supports for this system. I have a lot of hope with this solution because of that.
Okay, thanks.
If no one, then maybe I can ask a question. So I understand that your system is right now at the lab scale. Do you have plans to conduct some tests somewhere on Earth where you can find moon-like craters and you can test and see like its efficiency?
Anytime. It's no solution from few hundred years. It was first real industrial conveyor for transport bulk materials. It's not so difficult, but I'm open for any cooperation. Thank you.
Cool. Thank you very much. Thank you very much, Piotr. Please put your hands together for him. Our next presenter is Joshua Rasera from Imperial College London, and he will talk to us on application of the electrostatic traveling wave for particle size classification on the moon.
Well, thank you very much for, is this working? Yes, okay. Thank you very much for having me here today. I have the great honor of presenting the brilliant work of my colleague Yu, who completed his PhD a few years ago, or actually I guess just last year. So please bear in mind when you come to questions at the end that I don't even have the privilege of being one of the actual authors of this, so my technical knowledge might not be up to par. But you can definitely contact Yu with further questions at the end if they're super technical and I can't answer them. Anyhow, so what are we talking about today? Well, this is a sort of generic overview of an in-situ resource utilization flow sheet, which is very similar to terrestrial mining flow sheet. We have our excavation and haulage steps, followed by beneficiation and then extraction. Our research group primarily focuses on the beneficiation side of things. And in this presentation today, we're looking mostly at size sorting, particularly in a very novel application of something called the electrostatic traveling wave. Now, the electrostatic traveling wave, or ETW method, it's very clever. Essentially what we have is a printed circuit board with alternating poles that generate a static electrostatic field, or an electrostatic field that moves along the circuit board because the the poles are offset by about 120 degrees. In this case, we have 3 different poles. When we put particles onto the circuit board and we activate the system, the electrostatic field moves along the board, and the particles interact with that wave, or that moving electrostatic field, and they are conveyed along the surface. So this has been explored by a couple of different research groups for conveyance applications, and it works reasonably well. You can also use it for things like cleaning solar panels. If you embed electrodes into the surfaces of your solar arrays, you can just turn it on, and then your dust kind of moves off of the surface, allowing them to be clean. But the purpose of this study isn't so much to look at the transportation of particles, but more so to see if we can use this effect to separate particles by size. So how do we actually get, and this is a good demonstration of what we're trying to actually accomplish. So how do we actually get to this, though? So through UA's PhD, he did a phenomenally wonderful and extremely complicated set of mathematical modeling to try to describe the behavior of these particles and how they interact at a very fundamental level with these electrostatic fields. And if you're familiar at all with our research group at Imperial, how we generally go about studying things is by stripping it all back to very first principles, understanding exactly what is going on from a physics perspective, and then doing limited small-scale experimental studies in order to validate the models that we've developed. We're in the center of London, we don't have a lot of lab space, so we have to be very creative with the approach that we take, and this is how we go about doing things. You can see here all of the different steps that UA went through in order to develop these these different model methods, and then the methods below that he actually applied. So we're just talking about little particles moving on the surface of a printed circuit board. At its surface level, this is not particularly complicated. But then you look at this, and clearly it is not a straightforward process. And as you'll see, there's a lot of things that can happen. So depending on your initial conditions, depending on the particle sizes, depending on the materials, depending on your frequencies and your voltages, you get different particle behaviors that you can see here. And so he's classified these into 4 different motion modes. So on the top left, we have curtain mode. And this is usually for very fine particles that tend to sort of float along the surface and they don't actually touch the circuit board. Then we have the hopping mode, which is more for larger particles at more moderate frequencies, and they tend to just sort of bounce along the surface of the board. The surfing mode, particle jumps up, and this is for very fine particles, and then just skids along the surface. And then finally, this vibration mode, which you can kind of see the little red dot kind of swirling around, and it's a very chaotic bit of motion, and it jumps up and down and moves around. And we actually do see all of these different modes of motion when we look at high-speed video footage of these particles. I don't have that in this presentation today, but if you're interested, just ask me afterwards and I can show you some videos. Something else that we found that is actually very impactful to how these particles perform in these separation or in these motion processes is their initial conditions. And so on the left-hand side, we looked at the differences in initial particle velocity into how it behaves in the type of motion mode that it moves into as the particles, or as the system starts operating. So you can see the green here represents a particle that's just stationary on the board, and then the red is a particle that has an initial velocity of 1 meter per second. And the behaviors that these particles demonstrate are quite different. So they're very sensitive to the initial conditions that we start with. Here are some other influences of frequency. So you can see on the bottom left, we have a plot that demonstrates the difference for a particle of 10 microns, how it moves and how it changes modes depending on the frequency, and how it kind of progresses through different motion types. And in the upper right-hand corner, we see a 3D graph that shows the relationship between the resulting velocity, the frequency, and the particle size. And it's not quite perfectly smooth, so there's definitely variability depending on, and there are local optimums, but there's no global optimum for any individual particle. So these are the different aspects that we can kind of take into consideration when we're starting to think about how we can separate particles by size. So here are some examples of this actually working, because it's one thing to actually talk about it, it's another thing to actually see this happen. So in these demonstrations, we're using 50 to 20 micron glass beads called Ballatini. This is not genuine lunar regolith, it is not lunar regolith simulant. We're just trying to use an ideal particle that will allow us to demonstrate how this would work. All of this technology would work the exact same way on the moon, and we have yet to test it with the better regolith particles that are more representative, but in order to demonstrate how it actually works and in order to do this complex modeling, using spherical particles is much more straightforward. So you can see here, as we increase the frequency, we have totally different particle behavior. And once this video ends, you can see all of them simultaneously. But at the lower frequencies, the particles travel with the wave towards one side. At the median frequency, we have particles that are moving kind of in both directions. And at the higher frequency, the particles primarily start moving backwards against the wave direction. And this is what we were really taking advantage of when we start thinking about particle size classification. So on the right-hand side here, you can see the results from 4 different test cases. And just to sort of simplify it down, we can collapse these results all down onto a single plot. So the dotted lines are all the backwards motion of the particles, and the solid lines are the forward motions of the particles. And you can see that as the particles become finer and finer, the frequency that is needed to move them forward and backward shifts lower and lower. And when we tried then to mix together particles that have different size fractions, so in this case we have 30 to 50 micron and 75 to 110 micron particles, which we've now mixed together into a combination, or into a combined feed. And you can see the black line and the red lines are the initial particle size distributions for those individual size classes. We then see that the forward particles that are collected in the blue and in the purple, and the backwards particles in the red and in the yellow actually match quite well with the original size distributions that we see. And this is particularly impactful because the 30 to 50 micron range in this sort of sub 50 micron category of particles is very difficult to separate on Earth. And on the moon, when we're trying to think about different ways that we could potentially do size classification, doing things like sieving isn't really a great idea because the electrostatic environment tends to just cause blinding of your sieves, and it will just cause a lot of problems. But in this case, we can take advantage of that electrostatic environment, and we can actually see how we can do some size classification in this sort of notoriously complicated size range. So just to summarize and to have some final remarks, the electrostatic traveling wave method provides a particle transportation and separation capability depending on how we set it up. So you can either move all of your particles or you can separate them by size if you wish to. Particle motion has been modeled very comprehensively and classified into 4 different modes that I showed you earlier. The frequency and the initial velocity are identified as key parameters, and you can clearly see that in the previous slides that there's a massive impact onto how your particles behave depending on what these initial conditions are. The relationship between dielectrophoresis force and Coulomb force, which is really what drives the difference in behavior, whether moving forwards or backwards, and the wave frequency on particle motion have been demonstrated very clearly and comprehensively. The classification of particle mixtures into different size classes using this method has been demonstrated, and this is something that hasn't been done before. Although if you've seen my presentations at previous conferences, then you may have seen some of these results already, but it hasn't been done otherwise by other people. And finally, in future works, what we're going to look at doing is testing this with simulants and testing it in vacuum. Obviously, doing relevant environment testing is very important for the space, and so that's something that we definitely need to work on moving forwards. So thank you very much for your time. We'll give you 30 or 45 seconds back. But yes, if you have any questions, I'm happy to answer them. Otherwise, if they're very, very technical, you've got Yue's email up on this slide here, and you're welcome to contact him for more information. Thank you very much.
Thank you, Joshua. You've already made it clear not to ask too technical questions. So if we have not so technical questions in the room.
You can ask technical questions. I can try to answer them. Worst case, I'll just say I don't know.
Thanks, Joshua, for this wonderful talk.
Thanks.
Of course, I realize it's not directly your work. I was very interested in kind of what you expect to happen when you have these multi-mineral lunar regolith faces that are very rugged, and then you may have kind of interconnecting and bridging and so on and so on. And also, I saw research out of Japan that was also working on this, also in the zero-G, different gravity environments, which were very fascinated, which I kind of showed to my students.
Yep.
And how would you connect that to your work? Like, you're going to plan to do also zero-G on this? Or?
So I'll answer the second question first. With respect to zero-G, that's not something that we've thought about testing yet, or we briefly considered applying for one of the flyer thesis sort of things, I think, a few years ago, but haven't ended up actually doing that. I think the first step before testing it in zero-G for us would be more the testing it with more realistic materials, and then potentially in vacuum, and then maybe 0G, or at least lunar gravity. And in terms of the differences when we have real materials, that is a complicated one. I would expect the behavior to be different, both because of the mineralogy, but also because of the particle shape. The fact that we used spheres simplifies things greatly. And when you stop using spheres, then you've got more friction, and you've got different particle interaction modes, and that I think would definitely change the behavior of the material. I don't recall if UA modeled different materials or different particle shapes. I think it was mostly just spheres. But if you would like more information on that, you're welcome to contact him.
Yeah, thanks.
We have another question at the back.
Hi, thank you for the talk. Is there an upper limit to the particle size that you can move? Because you showed something around 100 microns and less. Is there an upper limit? And the second question is, did you look into how your surface of your circuit board changes? Is there abrasion? Can you see it? Did you check that?
So because we used spherical particles, and they were just glass beads, we didn't look at the change in the surface of the boards at all. I can't imagine there was much of an impact. I would imagine that with more abrasive materials, there would be some sort of impact, and that would be something that would impact the separation performance and the behavior of the particles overall. And sorry, your first question was?
If there's an upper size, upper particle size.
Let's see, what do we show here? So up to here, so he tested up to, I think, 350 micron, maybe a little bit bigger. So I don't know if there is an upper size limit. It's probably ultimately dictated by the particle mass and the resulting forces from the surface charge of the dielectrophoresis force and the interaction with the electrostatic field. So on the moon, you would have obviously a much larger upper size than you do on Earth, but on Earth, I think this is the sort of limit that we tested. So potentially larger, but I'm not exactly sure what it would be.
Thank you.
You're welcome.
Yes, please, go ahead.
Just one doubt, in the moon you will be in the middle of a plasma, so you will excite magnetohydrodynamic waves in your system. Do you expect some coupling between the dust and the plasma?
I don't know. That's something that I'm not really sure about, and beyond my sort of level of technical knowledge for this particular problem. So I'm not sure. You would have to ask UA. Thank you.
This one question at the back.
So on the practical side, as I understand, you propose your method to actually sorting the particles, yeah? Have you considered also to use as one of the technique for the dust mitigation? Or?
Yeah, so we didn't look at it for dust mitigation applications, but that has been one of the main studies, especially at NASA. I know Kennedy Space Center has done a lot of work in recent years about using not necessarily three-phase systems for moving dust, but using binary or two-phase systems to actually just remove dust from surfaces. And they've had a lot of success with that. So there is a lot of work in this area. It's not something that we focused on particularly with this study.
Thank you.
I think that's good.
Great. Thank you.
Thank you very much. Thank you very much, Joshua. Please let us thank Joshua once again. Our next presenter is Xiaochen Zhang from ESRIC, and she'll be talking to us on design of a continuous lunar regolith particle size classification system.
All right, good evening, and thank you for staying until the end of the day. I will be continuing on the topic of lunar regolith particle size classification, but from a different approach. So this is a conical particle separation concept that we adapted from literature. The process is quite simple. You just feed a particle mixture like simulants onto a rotating cone with a textured surface, and when the particles start to hit the cone and travel down, the larger particles will leave the cone first and also settle a bit farther away, while the smaller particles, having a larger surface area to mass ratio will be delayed in this process and settle later in this rotational path and also stay closer to the cone. This is a schematic drawing summarizing from the two reference literature pieces. And some of the major features about the system include the separation is basically done with gravity and the centrifugal force generated from the spinning cone. And it works in the fluid-free media, so we don't need water or gas that's commonly required for terrestrial applications. The components are adjustable and include, as well as the operational settings. And in theory, there is no limit on the particle size in the incoming feedstock. And also, the products can be classified into several size ranges simultaneously, although the separation limits still need to be explored. Last but not least, it is possible to operate the system continuously and therefore reduce the need for a human intervention. But now the question is, how can we design the system to control the performance and achieve a separation goal that we set? So we started to build our own versions of the system using 3D printed parts like you saw earlier, and we began with testing some operational parameter effects on the separation results. Here I present you two examples. On the left, when we had the cone rotating at a rather low speed, we saw the particles, a lot of them got stuck on the cone between the 3D printed layers, and the other ones that get to leave the cone stayed very close to it. But when we raised the speed to a much higher setting, most of the particles got released from the cone and also spread to much further distances. And as a result, we can analyze the concentration of our target particle ranges around the cone to determine where to separate and collect. And this is an example where we tried separating a mixture at 1 millimeter. The system configuration operation is important, but we also wanted to know if the system is sensitive to different particle types of different properties, basically. So here I present you another example when we tried to compare the separation results between two particles of different shapes. So we got simulants from off-planet research, and they're both in this one, they're both the highland type, but on the bottom here, we used the normal OPR-H2N simulant without agglutinates. We also got the agglutinated type that's shown in the top two images, and you can see they have very different particle shapes. We sieved the simulants into different narrower size fractions and ran them on the same system and to see if within the same size range, will they distribute into the same collection zones between the two particle types. And this is what we found. So let's see. Yeah, so in the larger, for the larger particles, which are represented by the striped columns on the graph, they're mostly concentrated. The highest concentration was found in the first zone right after the feeding position, which is expected. And similarly, the smaller fractions, which are represented by the solid columns, started concentrating from the second zone. But between the two particle shapes in the same size range, we saw that the agglutinated particles, which are the yellow columns on the graph, have a much wider distribution pattern, which means they are less concentrated in the same collection zone. And this is especially significant in the smaller size range, which is, the solid columns here. So, so knowing the system configuration is not important. It's not enough. It is equally important to know the material we're handling to calibrate our system accordingly. Now, from literature and our experiment results, we summarized this table containing some factors that we think have influence on the separation performance. But if we are given these parameters, how can we predict where a particle would land after interacting with the system? So following an example discussed in one of the reference papers by Mitchell et al., we started developing our own version of a mathematical model. The clicker is not working, unfortunately. There we go. So we started by assuming a single particle, spherical particle rolling down from a rotating cone surface, and assuming it's traveling in a straight line, and the cone is not inclined, it's rotating horizontally. And we looked for the acceleration of the particle when it's traveling down the cone surface, and the exit velocity when it leaves the cone, and also the time of free fall. And we found that all three factors would depend on the gravity and some dimensions and the system configuration, and of course the cone speed as well. But for the material property, we only found that is relevant to the friction coefficient. And of course, this is the rolling model, so in reality, we need to also consider sliding and tumbling and other kinds of interactions with the cone that will have a similar effect. So this friction in reality would depend on the particle size, the particle shape, morphology, and also the cone surface roughness. So we need to calibrate a model to have a representative friction effect between the particle and the cone material. Just to illustrate the difference of different friction coefficients. In our mathematical model, we assigned 4 particles of each have a different friction coefficient, rolling down starting from the same position on the cone that's marked by the yellow star here, and if the friction coefficient is higher, then it will take a bit longer for the particle to roll down and land on the collection zone. But because this is based on the rolling model, under terrestrial gravity, all 4 of them will land in somewhat similar positions. But if we change the gravity setting into a lunar gravity, much lower, we see the difference became much more magnified. So if we want to achieve the same separation targets between Earth and the Moon, we'll probably need to make a lot of adjustments in the system configuration to meet the same targets. So just to summarize our current progress, we tested this separation concept in the ambient environment, and we built a preliminary mathematical model. We've identified several factors that will influence the separation results, and also the system is currently thought to be scalable and customizable to meet different separation targets. But in order to precisely calculate and predict the separation patterns, we'll need to continue our experiments and improve the mathematical model. And we are also building DEM simulations for both single particle and bulk particle material types. And in parallel, we are also investigating in the material properties. So we're doing a lot of characterization in the lab on our simulants and compare it with real lunar regolith data in order to calibrate our models. And we are also planning some tests in lunar-like environments. This includes in our vacuum chamber in the lab and also on a reduced gravity platform. So hopefully next year I get to come back on stage to share more exciting updates. Just a closing message before cocktail time. We designed this kind of particle size classification in order to provide feedstock for, let's say, other ISRU downstream applications. But what is actually needed by the users? Well, earlier, David presented a figure related to additive manufacturing. Thank you very much. I also found some example literatures in additive manufacturing. And as you can see, some of them did mentioned that in order to do their experiments, they kind of like sieved or reduced the feedstock particle size. Some of them did not specify a range. And there are also several literature that we found that mentions that particle size is important for their ISRU activities, but they're not yet sure on the exact range. So for the audience members, if you have any valuable input, and like if you could let us know if you have any specific requirements on your particle size for your ISRU studies, could you please kindly let us know so we can design a system to provide materials for you in the future. So that is all from me. Thank you very much. If you want to discuss, I'll be here tomorrow, or you can also connect with me on LinkedIn or emails to stay in touch. Thank you.
Thank you very much, Xiaochen. Do we have questions in the room? No, I think everyone just wants to go to the bar. No, we have a question, please.
Thanks so much. So I wanted to open it up because I know a lot of, maybe there's sessions tomorrow on additive manufacturing, but regarding your questions on particle size requirements for additive manufacturing. So my personal opinion on that would be that you want it to be as small as possible to create at least layers or some kind of deposition that is homogeneous in the conditions you're going to work at. So mainly our community works currently in the Earth-based conditions. There's now multiple efforts that we're trying to kind of simulate these, for example, lunar conditions more. And it's all about kind of getting a small particle size to have, for example, higher sintering activity, and then, but still getting flowability, right? So I think the size sorting is very, 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 very important in the beneficiation, and I'm really happy that this work is happening. Sorry.
Yes. Can we get the mic here, please? Yep.
I would guess that it doesn't depend only on the size of the particles, but the distribution of mass inside the particle. Because basically friction will go with R square of any particle, but the weight will go with the mass, with this R cube if it is dense. But if it is a fractal, the dust grain, it will scale with a power that is less than 3. So basically different types of dust, I would guess, will be separated differently depending on their topology for the same size.
Do we have more questions? No? Thank you. No problem with that. Thank you so much, Xiaochen. With that, we conclude the session and conclude today's conference proceedings. I once again thank all our wonderful speakers and the audience for your engagement. And now I pass it on to Lisa.
Thank you very much. Thank you. Thank you very much. Thank you for still being here. And now there is an event at Melusina. There's a couple of ways to get there. You can walk. It's a nice dry day and plenty of conversation to be had on the way. There's also free public transport in Luxembourg, and I suggest you definitely look into that because taxis are most definitely not free in Luxembourg. So look into free public transport. We have an app called Mobilitate, and that will send you all sorts of different routes, and there are a variety of options. Or find somebody with a car and they will take you there as well. So have a lot of fun and be back here bright and early tomorrow morning for the last day of Space Resources Week. And thank you for still being here in the room, and thank you to all of our speakers and a fabulous, very, very dynamic audience with plenty of questions. So with that, good evening.